Right, container scheduling. How many people understand container scheduling? Okay, I'm hoping that you'll understand it a bit better at the end then. So, container scheduling, practical guide. There's going to be a demo. The demo I sweated blood over the last day or so. And hopefully that's going to work. I think it will work. And I'm hoping it's going to be interesting and informative. It's going to probably raise a lot of questions in your head about how this stuff works, but I'm hoping things will ultimately get much clearer as Kubernetes develops and progresses. And we're going to start off with talking about Borg. Some of you may have seen that bit from my talks before, or may have seen John Willis talk about it. Because basically I stole his slides from him. John Wilkes, sorry, not John Willis, John Wilkes. This is me. You can get me on TechGirl, or you can get me on Google Plus or Plus Mandy Waite. How many of you use Google Plus? So, now I want to know, why did you laugh when I said that? Come on, why? I didn't say it with any kind of form of irony, and you still laughed. It's like, what's going on here? And that's me wearing my Google I/O 2014 Italian soccer jersey. I'm hoping to get another one this year. So yeah, we're going to talk about Borg, and I normally start with a picture of a data center and say, what's this? And we're not going to do that. But I want to talk about Borg because we can talk about Borg, and we couldn't talk about Borg before. We couldn't even use the term Borg in talks because Paramount Pictures would sue us. But I think things are a bit better nowadays. And how many of you know where the term Borg, the original name for Kubernetes comes from? You never heard that story? Was that? No, maybe not. No, sorry, I'll tell you later then. I'll get to it. Okay, all right, so this is Borg, and Borg is our cluster scheduler that looks very much like Kubernetes. And most of you know that what we're trying to do with Kubernetes is make this kind of thing that we do internally available to everybody, and not necessarily at Google scale. This isn't a Google scale thing, right? We want everybody to be able to do this at small scales as well as big scales. So it's a little bit of a different problem for doing it externally outside Google, because we have a lot of machines and we have a lot of traffic. So Borg basically consists of this thing called a Borg master inside a cell. So we have many of these because we have many cells. Each cluster that we have, cluster is effectively a data center, is divided up into cells. Cells are about 10,000 machines, and at the heart of each one of these cells, probably not in the middle, probably somewhere on the edge, somewhere in the corner or something like that, but we have a Borg master, and that's replicated multiple times for robustness and resilience and all of that. And it basically talks to machines, our fleet of machines. We have machines that aren't controlled by Borg, but they're normally separated, kind of ring-fenced away, because they run foreign stuff that we have to run, but we don't really want to run on top of everything else. So we have, ultimately, this system that will take all of the work that our software engineers do and schedule it on the machines that can run it. So the idea was ultimately that we didn't want engineers to have to worry about choosing a rack in a data center somewhere and SSH into that machine, or SFTP-ing a binary over to that machine, SSHing into it and then bringing up that binary, maybe doing that many times. So the idea will be that they'll write a configuration script which looks like this. I used to animate this, but now it's just a plain configuration script. And they'll build a binary, distributed build system, which is available externally as on GitHub as Bazel, B-A-Z, B-A-Z. Yeah, I'm becoming very Americanized. I even say tomato now. I used to think tomato sounded really terrible. Now I say tomato all the time. It's horrible. It's so sad. Our binaries are statically linked, as everything's kind of moving back towards statically linked, right? Dynamic linking was all the thing, and now everything's being statically linked again. And it has a web server in it as well. We can define arguments. We can set resource requirements in terms of RAM and disk and CPU. We can also say how many copies of it we want. All this look very familiar, right? This is very familiar to anybody who's developing Kubernetes today. So we can do all of this, and that's good. So ultimately what engineers would do, they would submit their configuration file to Borg, what we saw earlier, stored in persistent store, Paxos based, not Raft based like in Kubernetes and etcd. And ultimately, at some point after some period of time, in this case 2 minutes 40 seconds, we'd see roughly about 10,000 of those tasks running. So a job is, an instance of a job is a task. And so we get to a point where we have 10,000 running, and roughly 10,000 running, which is interesting, right? Roughly. And we'll talk about that in a second. So it ends up like this. We've run our Hello World job, and this is Hello World for the data center, right? So I'm going to do this live one day. So I know I can. I don't have any real privileges because I don't work as a SWE by day to day, but I could do this very, very low priority. Okay, and that's the key. That's what we're talking about scheduling for. I could do this today, but the scheduler will say, "Yeah, I don't care about her. I'm going to run this when I can. It may take a while to run, it may not do." And ultimately, we use containers. We use a format that's been published externally as LMCTFY, or let me containerize that for you. Anybody familiar with LMCTFY? Okay, a few of you. So we actually published that. That's on GitHub as well. So it's a very lightweight container format, and that's what we did C groups and namespaces for. It's not Docker, right? So it's much lighter weight than Docker. And I'm not going to say bad things about Docker today. I'm not, really, ever. Anybody from Docker here? Okay, I'm safe. And John Wilkes basically said this. We don't use virtual machines, we just use containers, and we pack multiple tasks into one machine. And we try to make sure that they don't tread on each other, because we don't want your bit of Gmail that's servicing your email to be trod on by something else. And that's important. That's a scheduling task. All of these things we're talking about are scheduling tasks, right? And this is why it's all important. And Kubernetes may look like Docker Swarm today, but it's not. It's a scheduler. It's going to be effectively transformative in what it does for us. It's going to change the way we think about computing. It's going to be the new infrastructure. Ultimately, the idea of a node will go away. The idea of a virtual machine will go away, and we'll replace it by this thing that's called a scheduler that sees maybe a machine as a resource boundary initially, but at some point in time, even that will go away as we get faster and faster connectivity. We can start. We're doing RDMA over converged Ethernet now, so we can talk to memory really quickly. Soon we'll be able to grow machines vertically just by linking them together. So we can run very, very big workloads on what's effectively a single machine, which is the data center. And ultimately, we have this. We get to a situation where after 2 minutes 40 seconds, again, it takes a while to ramp up. We cold start this a little bit. We take a while because we don't want it to all burst into life at once. And we have to transfer a lot of data around as well, because that binary is like 30 megabytes in size, 10,000 copies of it. It's going to bit of shifting around the data there. So we get to a point where we have 9,993 running. And the reason is because of failures. Those 7 missing. Okay? Seem really important, but 10,000, not so bad, right? It's a decimal point when you have like 10 running. And the reason for this is because we have failures. We have various reasons why something might not be running. At the top here on the bar, we have production, and then we have non-production at the bottom. So we're looking at failures for production, which are very small. We might shut down a machine. And then it's down to the schedulers to say, okay, whatever's running on this machine needs to be run somewhere else. We may drain that machine. I'm not really quite sure how that works, but we may drain it. But ultimately, most of the production failures, and I'm using it in quotes, occur because of machine shutdowns. And it's very unlikely that a production job will be preempted, which is what that big grey bar is at the bottom, preemption. So basically, things that were running end up stop being running. Now you kind of start thinking about this like the process scheduler on a Linux system, right? So it's the same kind of thing. We have preemption going on all the time. Lower priority jobs are being kicked off by higher priority jobs. And priorities sometimes change as something gets starved of resources. Its priority may go up, and ultimately may come back on and kick something off, and it will go through that same cycle. It's a kind of similar thing to that. So we have these low priority non-production jobs. And what are they? They're things like batch jobs or map reducers. Things that we want to run ultimately at some point, but we're not particularly bothered about when it happens. We may have some concerns, but we want to ultimately have them run to completion. But we don't want to dedicate all of our clusters for them to get it done. We can do this over time, and we'll see some strategies on how that works. And ultimately, failures are pretty normal for us. Fighting against it is pointless. Fighting against the fact that your hardware may break, or something may go wrong, or a rabbit might eat your fiber optic cable coming into your data center is just not possible. And that happened, I think, right? A rabbit ate, was it a rabbit or a rat? I'm not sure. Something ate through one of our fiber optic cables once. It may have been somebody else. It may have been a Facebook employee or something. It wouldn't have been a Facebook. They're friends. They're good guys. They're just down the road. So ultimately, things break, and we have task exits, and they have to be fixed. And our software is designed in order to be resilient and to not worry about that. So, yeah, it's broken, we'll run it somewhere else, no problem. We don't have panic stations, we don't have alarm bells going off. We will have some guy probably wearing Bermuda shorts and a Hawaiian t-shirt go in there, which is going to be really hot, and ultimately fix the hardware. But it's not going to be bothering us because we won't be panicking about it. It'll just be part of normal business. And one other thing that we talk about is efficiency. And efficiency, again, is another scheduling thing. Everything is scheduling. It's all about scheduling. And how do we say it in England? Do we say scheduling or scheduling? I don't know. I've lost track. I no longer know whether it's scheduling or scheduling. So I may switch between the two. So we have a fleet of machines, and we could potentially end up with parts of those machines not being used, like lots of expensive memory or lots of expensive CPU. And this here is virtual machines. All of these bars are virtual machines. And at the top we have CPU, at the bottom we have memory. And so this is utilization. This is actually compute engine virtual machines running as jobs on Borg. They run as jobs on Borg. They are running it in a container. So whenever you get a virtual machine, a GCE instance, it's a container, effectively. So what we see here is one machine, and we can look at various different patterns on here that we can see and call out some interesting things. Here we have a place where we have CPU and memory available on that machine, on different machines, and that's reusable. We can use that stuff, right? But there's also the case where we have this, where we have places where we have CPU available and we don't have memory available, or places where we have memory available and no CPU available. So that's effectively called resource stranding. When your CPU is saturated and your memory is half used, all of that rest of that memory is wasted, effectively. So we had to have extremely efficient bin packing algorithms to try to match up work with particular machines. So we can actually, I mean, I've got the Tetris thing. I mean, Kelsey and I did the Tetris thing on the same day. So he did it at Software Circus and I did it at Container Camp. But basically, we can think about it as a Tetris. We're trying to match up a workload of a particular shape with a gap on a machine of a particular shape. And it's a good demo, but I'm not going to do it today because I don't know why. I just decided not to do it. But you can imagine what it's like, right? That's bin packing for you. And please stop me if you have any questions. So this is from 2014, this data. This is in the Borg paper as well. There's a Borg white paper that talks about all this stuff. And that calls it out in more detail, stranded resources. And also efficiency. We run multiple tasks per machine, which doesn't sound particularly incredible, but it is extremely important to us. The median average is about 9 tasks per machine. So this is quite important to us. And also the fact that we run both prod and non-production tasks on the same cells. We don't have dedicated cells for non-production workloads or dedicated cells for production workloads. So your Gmail, your video, your web searches are all running on the same cells as our batch jobs, our map producers and our batch jobs. And ultimately, we see the cell as a single resource, a big resource with lots of different types of things running it. The blue bars here are production jobs, and the grey ones are non-production jobs. And the grey ones may be preempted quite frequently, as we saw from the previous graph, and that's interesting. All right? And just quickly, what we get from actually sharing ourselves between production and non-production is something like this. So we start off with a shared cell. This is a shared cell with production and non-production tasks. And then we click the button and nothing happens. We can compact that to the minimum number of machines it would take to run that workload, all of that work. What's the minimum number of machines we would need? And that's it, a shared cell compacted down. And we took individual cells, which were running those workloads, the bottom blue bar being production, the grey at the top being non-production, and then we tried to compress them, we would end up, oh, I haven't got the compressing thing on there. Okay, there should be a line there, so it won't compress very far, effectively. So basically, you'll find this compresses about that far. So my line should be there, and the arrow should be there. But it doesn't compress anywhere near as much as it would do if we were running both non-production and production tasks on the same machines. All right, okay, so that's important, and that's what we're going to talk about on the next slide, which is this one. And this it's starting to get back into what Kubernetes does today. So we saw earlier on the configuration file that we can specify the amount of CPU, RAM, and disk that a job or a task, an individual task can have. And in real life, it looks much more like this, the actual running workload. So it's like this. It's very erratic, very hard to follow. And the line at the top is the line that basically represents what the declarative thing that we said in the configuration file matches. So that grey bar is everything on all of the jobs that are running that's in the configuration file itself. So the reality is a lot different. And we have all of that resources wasted at the top there. That top between that top bar and the actual usage is wasted effectively because we're not oversubscribing. And what we can do, what we do in Borg currently is we calculate a reservation. We use an algorithm to predict how much resource that's going to need over time, and we effectively calculate this reservation. And that's the blue line here. And what that gives us is, we think, well, what that really means is we think this process isn't going to use more than this. We could be wrong sometimes. Most of the time as the algorithm gets better, we're right. But we have this overhead, effectively, that we can now reclaim and reuse for other things. So this is now potentially reusable resources, this green stuff. We can now use this to run batch jobs. So now it starts to make sense why it's better to run prod and non-prod on the same cell, because we can actually stick all of the batch jobs in that green area there. Okay, and we can run them at a very low priority. So if something of your Gmail task at the bottom there suddenly needs more memory, we can just kick it off the machine, okay, and get it back. That's how preemption does. Yep. I don't know the answer to that, and I wish I did, because I should know the answer to it. But I will find out, and next time I talk about this, I'll let you know. But follow up with me on Twitter or something, and I'll find out. But yeah, it's something that's been weighing heavily on my head, because there's got to be a reasonably predictable, reasonably good science to make understanding what it is your expectations are from your running services. Most of it's going to come from experience, but we must have better algorithms than just experience, right? Yep. Demo. So we'll talk about when we get to Kubernetes. Okay. All right. So resource reclamation. That's effectively reclaiming resources. And we have some. We did an experiment back in 2013. We had the reservation, which is this yellow. So the reservation is the top of the yellow graph. The grey is effectively that grey line, and the bottom one is the actual utilization. And so we have this big space, which is that overhead, which would have been here before, in this bit. Who's hidden behind the pillar? Anybody hidden behind the pillar? No. So this bit here is effectively that yellow bit. Okay, so we could compress that a little bit. We could play with the algorithms and make it smaller. And so that's exactly what we did. Experiment, we reduced that reservation, made it a little bit tighter and much more aggressive, and we saw much more out of memories. And out of memories are really the currency of scheduling when it comes to memory. We saw lots more out of memory errors. And so we creeped it back up again to a point where we got less. The spike at the end is a glitch in the experiment, which I don't know the details of, but it wasn't actually anything to do with the experiment. It was just something that happened during the experiment. But we see that we have much less OOMs now than we used to, and we're kind of closer to the baseline. So having done that experiment, we decided to roll back to where we were before, did some more testing, and ultimately rolled out the one from the middle, this one here, to production. So basically just experimenting. And now we've got more resources back that we can reuse for batch jobs. So this is really making efficient use of our fleet of machines. And this is all in the wallpaper, if you want to read more about it. Okay? So on to Kubernetes. Normally at this point I say, how many of you know what Kubernetes is? I don't have to do that today. It's fantastic, right? Does anybody doesn't know what? No. Okay. So yeah, how many of you know how to say it yet? How many of you can say it properly? You know, you're thinking, right? So I always offer to see me outside afterwards, and I'll give you some training on how to say Kubernetes. It's a very Japanese word, Kubernetes. Right. So Kubernetes looks kind of similar to what we looked at before. Is that we don't have high availability on the master. Okay. And we should have high availability on the master, right? So what am I going to talk about next? I know what I'm going to talk about. So this kind of, much of my preparation for this was done on the demo when I should have been preparing my talk. So it may get interesting. So I may be surprised by my slides. Never be surprised by your slides, right? Never, ever, right? It's like your next slide comes up and there's like 3 bullet points and there's that last bullet point at the end, which you thought, yeah, I don't know. And now you're stuck on it because it's there and everybody's reading it and everybody's looking at it saying, oh, I've got to explain it. Oh no, how do I explain that? It's terrible. Or just a complete slide which you don't know what to say on. Don't do it, just delete them, right? Delete the bullet point, delete the slides, don't have them in there. If you can't talk about it, just don't do it. Right, so this is Kubernetes. You know that already, right? And we can kind of simplify this, and we're gonna have a demonstration in a minute with the world's worst Kubernetes cluster. So that's gonna be really cool, right? What? You've got such high expectations, you people. Right, so we have a KX master with some of the stuff removed. We have nothing on our nodes, so we have some stuff running on our nodes, but maybe they're empty. And we have a scheduler, and we have a controllers, and we have an API server, and we have etcd. And what happens if we take the scheduler away? What happens if we take the scheduler away? Anybody know? Is that? Yeah, so, well, that's nearly true. We can't schedule pods now. We can't schedule our pods. We can't schedule resources, not just pods. We need a scheduler, effectively. But there is an exception to that, because basically we specified a node name in your configuration file. You're basically saying, I want it to run on this node. And this is done before it even gets to the scheduler. So if you specified a node name, it will be scheduled on the node that you specified. So you could actually do all this. You could be that engineer who has to SFTP a binary by specifying exactly the machine name that you want it to run on. You can do that. You don't want to do that, right? So what do we need? We need a scheduler. I should do that, shouldn't I? What do we need? Awesome. You're a good audience saver. Right, so resources. Let's talk about resources. And this is where it gets fun. So this is what my nightmare of a night was like. So yeah, this is a picture of CPUs and memory. It cost me £10 from iStock Photo or something like that. They're really expensive, their photos. So a resource is something that can be requested, allocated, or consumed effectively by a pod or a container. So we have CPU, we have memory, and CPU is specified in units of cores, as you know by now. How many of you have done resource limits on Kubernetes at all? Not many of you, okay. So maybe afterwards you'll go off and run off and do this, because it's going to be quite interesting. Maybe you'll be able to recreate the complete disaster of my demo yourself. So CPU specified in units of cores, and what that is currently really depends on what the provider is. You know, it could be like a ZX Spectrum, or you could be running on a Raspberry Pi cluster, in which case your expectations of what a CPU is might be a little bit less than if they were running on an Amazon instance, or an EC2 instance, or a Google Cloud Platform instance. Memory is specified in units of bytes. CPU is compressible. So effectively that means it has a rate and you can limit it. You can stop it from having more than it needs. So it's compressible. And memory is incompressible. So you can't do that with memory. You can't say, I'm going to stop you once you've used 2 gigs of RAM. You can't do that. You can say, if you try to use more than 2 gigs of RAM, I'm going to kick you off the machine. But you can't actually throttle it. Okay? That's an important distinction. So CPU and memory is different, much different when it comes to scheduling. I'm not going to do too much on memory today. I'm going to try something and see if it works, and we'll see. In the future, we're going to have more resources, things like network ops, bandwidth, storage. Storage is incompressible as well, interestingly. All the rest are compressible, IOPS, storage time. And ultimately have a Kubernetes compute unit, a KCU, which should be able to understand the differences of what it's running on. I'm not sure how that's going to work currently, but it would mean that when you specify one KCU, it should be the same regardless of where you run it. And ultimately, resource-based scheduling, scheduling's easier to say actually. I'm going to go with scheduling. No. Spec. So we specify here in the spec for the container. Effectively, it's a container level currently, not pod level. Will be pod level in the future, apparently. So we can specify resources like we did before in the previous configuration file on Borg. Memory, CPU, we can specify requests and limits. So that's an interesting point, which we're going to talk about shortly. What is the difference between a request and a limit? Anybody know what it is? Come on, give the talk. Give my demo for me. So Resource-based scheduling, which is currently a work in progress, and your mileage may vary, and some of my talk kind of goes from what we have today with 1.1 and what's going to be in 1.2 and what's going to be there in the future. But this is what we have currently. So resource-based scheduling effectively provides quality of service for scheduled pods. And this is all per container, CPU and memory requirements will be pod in the future as well. And you specify a request and a limit, and as I said, future releases are going to support it better. So currently we have a request and a limit. We can set them differently. The expectation is that limit will always be greater or equal to the request. If you say, I request a certain amount, you're basically saying to the scheduler, only put this on a node if that much of this resource is available. So if you ask for 1 core as a request, the scheduler has to make sure there's 1 core available to run that. That's basically your minimum requirement to run this work, okay? The scheduler won't schedule it if it can't meet that request. So it will sit in the queue, pending, waiting for resources to become available. And with things like Jobs API, that will ultimately work now, because things will run to completion, then you have more resources available, and you'll be able to schedule it. And we can have situations where request equals 0. When you say request equals 0, you're saying, yeah, I want this to run, but don't prioritize it. Just give it memory when it's available. That's good. That's the best effort guarantee. It's the lowest of the quality of service levels. Then there's also burstable. Burstable is when the request is less than the limit. Now the limit is more of a runtime instruction. You're basically saying this is the maximum you should give this pod, or this container effectively. This container, and then you should stop it. You should either throttle it or you should kick it off. Now it's interestingly different with CPU, as we're going to see shortly, because CPU is by default share-based and not quota-based. So we have some interesting compromises to make here. And that's burstable, that's a middle quality of service tier. Then we also have guaranteed, where the request equals the limit. You're saying the minimum I want is the maximum I want. I want you to give it all of this stuff. And that's going to be guaranteed. So you're saying, only schedule this if it's available, and when you're giving it to it, make sure it always has it, effectively. That's what you're saying, right? Okay, and through best effort scheduling, apparently, and again, this isn't personal experience, this is what I've heard, is that for low priority workloads, effectively improves utilization at Google by 20%. Okay? That's really important, right? And 20% in Google terms is 2 data centers, or something like that. Yeah, it's some crazy number. So scheduling pods on nodes, I should do a demo, right? Well, I'll do a demo. I'm going to have to sit down now. So, glasses off. First we go to this one, right? So this is the world's worst Kubernetes cluster. All right? And it's basically a kubelet. And it's the only way I could make it work currently. So what we're looking at here is quotas and not share-based. So we're going to look at CPU when we're doing quotas with requests and limits. Okay? And in a minute we'll look at what that looks like with shares. Because they're kind of different. So what do we have here currently? Nothing, hopefully. And I've got this is one of the most secure virtual machines you're ever going to see. I can't run any commands on it apart from Docker and kubectl. Really, I can't do anything more than that. It's crazy. So Docker PS, we have nothing there. And what we're going to do is take some of these YAML files that I've got created earlier. I spent all morning doing, and they're not particularly complicated ones, but trying to get the balance right was interesting. So this one is a pod. It's going to run a CPU hog, effectively. It's going to MD5 sum on /dev urandom, which is going to consume all of the CPU. And we're going to say, oh, this one is not the one I'm going to run first. So it's going to run busybox as well. But there's another one I'm going to run first, which is the BE one. And this one is the same, except its request is equal 0. So that's best effort, right? Same one we saw before. But it has a limit as well. So his limit is 500. That's the maximum we're going to give it. But it's said 0, run me as a low priority, effectively. So what does that mean, effectively, in a quota-based system? And we're going to copy that into our manifest directory. And see what happens. So, after a second or two, normally longer than I'd like, run, container run. What's it doing over there? It will work. And there it is, right? So now we have a container scheduled. How many of you know what an infrastructure container is? Somebody asked me this question today. You know what one is? Okay, cool. Excellent. Anybody else? No? Okay, the pools. The pools container. Anybody know what that is? Tell me afterwards. Okay, cool. It's interesting. I like the pools container. Take a pause. Right. So we have a container running, and we'll run Docker stats. Have a look at what that's doing. I should be using CAdvisor, but I'm too lazy currently. So here we can see we're using half a CPU. Okay, this is the one we said, 0 for requests and half a CPU as a maximum limit. So it's using half a CPU. This is quota based, and that's good. It's running. And we'll take the next one, which is number 1. This has got 500 requests and 500 limit. So it's the same. So it's a high priority job effectively. And we copy that to manifests. Unfortunately, I've not quite worked out a way, even using watches yet, to make this refresh automatically. So I'm going to wait for it to start. And now we have 2. And this one asks for half a CPU, and the other one asks for half a CPU as a maximum. So they've both got half a CPU. This has got 2 CPUs in it, this machine, okay? I didn't explain that. Got 2 CPUs in it. So basically, that's not a problem so far. We have 1 CPU spare. So let's schedule another one of those bigger pods. We'll use CPU 2. And wait for a second for that one. Not long enough. And you can ask me about why it's the world's worst Kubernetes cluster in a minute, but you can see it is. Hey, it's only 32 minutes past. I've got 13 minutes yet. I'm very fussy about my time. You have to drag me off the stage, screaming and kicking. So now again, we've still got half a CPU left, so we see all 3 of them have scheduled okay. The next one is a big one, so we're going to oh, it's big. I moved it. I changed it to make it easier to do. And I screwed up completely. So this one is asking for 1 CPU, a guaranteed one. Okay. Do you think it's going to run or not? Who thinks it's going to run? Okay. Who thinks it's not going to run? Who's not sure? Okay. I think the majority of people are not sure. Okay. That's fair enough. So let's copy big CPU over. Big CPU to manifest. And, as if by magic, I'm too quick. I'm going to work out a way of doing this automatically. If anybody has any suggestions, because you guys are really bright anyway, so let me know. It started to schedule, but it's not quite there yet. Docker's still thinking about it. Right, so now we see it's running. Ah, interesting. Now we see one of the pods has hardly got anything at all, right? It did ask for 0, and now it's got 0, effectively. Because we're using 2 CPUs for both of those pods, for those other 3 pods. So it has nothing it can use. It will use anything that's spare. It will be given anything that's spare, but it's kind of limited. It will carry on running. It may have a problem here, and it may programmatically have some issues, but it will carry on running to completion because it's a low priority job. So we have the higher priority jobs. And that's how scheduling works when it comes to resources for CPU. And if I just removed all of those files. Memory is a little bit different. So I'm not going to do the memory demo because it's not going to help much. I'm going to make it better and do it more. But effectively what's going to happen with memory is that if you try to ask for too much memory, you're going to be kicked off the machine. So you're basically, you'll fire off an OOM. You have an OOM score, and depending on what your guarantee is, you'll have a high OOM score or a low OOM score. And the scheduler will the kernel will effectively decide what to do on it based on its OOM score. And effectively what it will do is it will throw a seg port and kick it off the machine. And then try to run it again probably. Okay, so that's that one. And the last one is, just to quickly show you what that's like on here, and which one does which. Yep. effectively die, right? Because it hasn't got any memory, but that's what your expectation was. I mean, if you want it to run all the time, we'll set the limit and the request the same, and then it can only be scheduled when that memory is available. And nothing else can take it away because we can't schedule another pod on there that's asking for more memory than it could. So basically we're doing the oversubscription, but if every job you have is guaranteed to run, then you're not going to be able to oversubscribe at all. So just make sure you get your priorities right when you schedule the job. So kubectl, I'm not going to get a chance to do this. I'm not going to get time to do it. How long have I got? 5 minutes. All right, I'm going to go through my slides. Anybody can come and see the rest of the demo later, but basically in a share-based system it works differently, and it's a little bit quirky, and it's hard to reason about, which is why I wanted to show quotas. Shares by default, I think we're moving to a situation where we have quotas by default, but at the moment it needs an extra flag to the kubelet to make it work. So it is a little bit more harder to reason about. So running through the slides quickly, and we will finish in time. Yeah, so we have the idea of nodes. Nodes have resources. They also have potentially disks. They may not have disk mounted, but they may have them mounted, because they may be being used by some other pod of some kind. They also have labels as well. So these are the characteristics of the scheduler cares about when it comes to scheduling pods on nodes. We can, as we've seen, ask what CPU and memory it requires. The scheduler will say what CPU memory it requires. If it can't satisfy that need, it will be stuck in a pending queue. What disk does it need? I meant to put my note. That's a really important note, that one, at the bottom there, and I didn't finish writing it. So I will finish writing it when I publish the slides. Because I forgot in the meantime, I forgot what it was, because I got interrupted. Anybody, you saw me hacking on my slides earlier, right? I write my slides on the fly. So what resources does it need? What disk does it need? If it needs a specific disk, there may be some restrictions. Google Cloud Platform, I forgot what it's called, Alan. I forgot what it's called, Alan. Google Cloud Platform. Compute Engine effectively has the ability to mount a disk, read-only on many, many different machines, but it can only mount it read-only on one. So if you want multiple writers to a GCE disk, you can only mount it on one machine. So the pod would have to be scheduled on that machine if it was already mounted. And there are also limits to EBS IDs that can be mounted. So those limits have to be taken into consideration by the scheduler. And ultimately, node selectors. So you can specify labels on your nodes. And it may be, in the future with Ubuntu or something like that, you use the location as a label. In this case, we're saying disk type equals SSD to indicate that this machine has an SSD disk. Maybe others do as well. And if your requirement is high-performance disk I/O, then you probably want it to run on those machines. And so you're basically saying your node selector disk type equals SSD is a requirement. And ultimately, we move to a thing called node affinity, which I'm not really going to talk about now. It's annotation-based. It will run side by side with node selector for a while before it goes away. It will be replaced by a field ultimately, but it allows you to be less specific and more general about the way you're deciding what nodes to schedule on. In this case, instance type equals high mem2 or high mem4. You want a lot of memory on this machine. Okay. Ranking potential nodes. Once we've basically filtered using all of those things that we looked at on the previous slides, we have to rank each individual node. Not each individual node, but each one that we got out of the filtering system. We may have found more than one that match, in which case we have to kind of rank them and decide which one to do. And there's different policies. We can specify, make sure that we put it on the pod, on the machine, on the node with the most free resource. We can make sure that we have pods in a replication controller distributed evenly across all of the nodes in a cluster. We can also try to balance CPU and memory, like bin packing, and that's the default. It was the default in 1.1, I'm not sure if it is in 1.2. And adding to the scheduler, I'm not going to be able to talk more about this because of the demo, but there is some links at the end here, and these slides will be shared in my canonical deck at the end. But you can extend the scheduler as well. Three ways. You can either add it to the scheduler and recompile. You can run your own scheduler process, either instead of the official one or alongside, or you can actually have another selector endpoint that can do selection based on other resources. So it's possible to extend this. And finally, we get into a mission control. And the mission control is stopping things from being scheduled in the first place. So these things will never hit the scheduler. And the admission controller sits on the API server, so when you make a request, if it thinks, if it needs to enforce admission control on it, it will basically say to you, no, I can't do that, I can't run it. It will never hit the scheduler. It's not the scheduler's decision. We just can't do this. It's like a policy almost. And we have different ones that we can use in this case, and these are all enabled by default in 1.2, including another one as well, which is persistent volume label. And finally, the resources for this talk. My canonical deck is that short link there, which I've spelt out: 1, little o, big R, big M, big S, 0, little r. Okay, so that's where my short link is. And there's all of these links as well. So once you get the top link, you can go ahead and look at the deck. And remember, it's open source. Contribute, contribute, contribute. Because the more you contribute, the more you can influence the direction of Kubernetes. Thank you very much. Cheers.
And we haven't actually got time for questions now, but you'll be around the rest of the afternoon?
I'll be here all afternoon. So, yeah.
So come and find Man.